Okay, so welcome back, and now we're going to do another example, and this time we're going to use the function sine x. And so we know from previous videos that the Maclaurin series that represents the function sine x is given here on the board as this series. So this is the nth Maclaurin series for the function sine x. And so what we want to do is, just like in the last example, we want to show that this converges and also converges to sine x. Okay, so again, we're going to apply the ratio test, but in order to apply the ratio test, let's consider what we have. And let me do it over here. Let me change. So we look at the ratio of the absolute values, right? So a sub n plus 1 over the absolute value of a sub n. Okay. And so if we look at this ratio, well, what do we end up with? Well, we're going to multiply by the reciprocal. Okay. So let's just write it out. And we get the absolute value of, well, since we're dealing with absolute values, we could just drop the -1 because it's going to be positive. So we're going to end up with this, and so we're going to end up with what? We're going to end up with x to the 2n plus 2 over 2n plus 2 factorial divided by x to the 2n plus 1 over 2n plus 1 factorial, right? Oh, wait a minute, I'm sorry. Hold up, it's n plus 1. It's n plus 1. Hold on, I put my 1 in the wrong spot. Let me just rewrite this so you guys can see it better. Because I goofed. So this is the absolute value of x 2 times n plus 1 plus 1. Okay, that's what I should have wrote. And so then the bottom is going to be the quantity, let me do it this way, 2 times n plus 1 plus 1 factorial. Okay, so that's what I wanted. Sorry about that. Okay, so now it's okay. So now if I simplify this, this is going to give me 2n plus 3. But I'm going to write this as a multiplication of the reciprocal. So this is going to be equal to x to the 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial over x to the 2n plus 1. Okay, so now we get to cancel some things. Okay, so here we got x to the 2n, and again this is a multiplication, so we can bring this absolute value together, okay? And then I can cancel these with these, and I'll have two x's left over. Okay, so this is going to equal the absolute value of, well, you know what, since this is positive and this is positive, I'm just going to write this as the absolute value of x squared. Okay, now here I've got a factorial. This is 2n plus 1 factorial, and this is 2n plus 3 factorial. So this is going to cancel all the factors except the first two. So I'm going to end up with the first two factors on the bottom. So it's going to be 2n plus 3 times 2n plus 2. And the rest of these are canceled by the factors in the numerator. And so this is what I have. Now, okay, so we do this, and now what we're going to do is take the limit. And it's obvious that this limit, right, so the limit as n approaches infinity of x, the absolute value of x squared, goes to 0 for all values of x, right? So that's obvious. And since that's true, and it's true for all x, right? So that means that we have found an interval of convergence of the entire number line, so all real numbers. Negative infinity to positive infinity. So now to show that the Maclaurin series converges to sine x, now we're going to look at the remainder. Okay? So we know the interval of convergence, right? And this is true for all x, so the interval of convergence is negative infinity to positive infinity. So now we've got the interval of convergence, and now we have to look at the remainder. Okay, so we're going to look at r sub x, r of x, or r sub n. What do I want to erase? Do I want to... Oh, let's leave this here. Okay, so now I'm going to look at the remainder. And for each x, there exists a real number c between 0 and x such that the following is true. Okay, so again, I'm just using what we've learned before. Okay, so we know that there has to exist some number c between 0 and x such that we have this. F of n plus 1 of c over n plus 1 factorial times the absolute value of, oops, not absolute value, x minus a oh no, I'm sorry, we're talking about Maclaurin series. Got it. So this is x. It's a Maclaurin series. So, okay. So we know that this has to be true, right? So for some value of c from 0 to x. Now, since we know, right, since we know where is it? Oh, since we know this, right, the absolute value of the nth derivative is less than or equal to 1, right? So we know the absolute value of, so this is the same reasoning that we did before when we were dealing with sine x. So n plus 1 of c is less than or equal to 1, then that means that this is bounded above by 1. And that's true for all n and all real numbers c. So that means what we have is now we can put these two together and say, well, if I take the absolute value of r sub n of x, that has to be less than what? It has to be less than x to the n plus 1 over n plus 1, absolute value. The absolute value of x to the n plus 1 power. And that's true for all real numbers x. And so then using this same idea as we did in the last video, the result is that the limit goes to 0. Okay? Because, again, I'll just write it out. So r sub n of x has to be less than how do I want to do that? Yeah, that'll work. So the absolute value of x to the n plus 1 over n plus 1 factorial, and it has to be greater than the negative of that. Okay? Now, again, using the squeeze theorem, if we take the limit of all of these, we find that the limit by the squeeze theorem of r sub x, or excuse me, r sub n of x is 0 for all values of x. And so thus, the Maclaurin series for sine x converges to sine x for all real numbers x. And that's it.